Section 1.10. In Section 1.10, we will consider various modelings with functions. In other words, we will begin to look at applications of all of the concepts, linear functions, nonlinear functions that we have considered in previous lessons. All right, so modeling with functions, what does that involve? Well, it really involves solving applications in the real world. Many real-world problems involve constructing mathematical models that are actually functions. However, in order to construct a function, we must be able to translate the verbal description into a mathematical representation, one which represents a mathematical model. In this section, you will learn to use verbal descriptions and formulas to obtain models involving both linear and nonlinear functions. Functions from verbal descriptions. So if you're given a verbal description of a real-world situation and you want to translate this into a mathematical model, well, first of all, let me say that there is no rigid step-by-step procedure that can be used to construct a function from a verbal description. However, there are some basic steps that must be taken. First of all, if you have a verbal description of a problem, the first thing you want to do is what? What would you do first? You would read the problem, read it very carefully, and in some instances, you might have to reread the problem 2 or 3 times. After reading the problem and understanding the statement of the problem, you then want to attempt to express the conditions given in terms of an independent variable x, which you will label as your unknown. So what do you know? Identify the unknown as your independent variable. Once you identify the unknown, the independent variable x, you then want to express all of the known quantities in terms of that independent variable. And then you're able to establish a mathematical relationship between the independent variable and the other quantities to derive a mathematical or an algebraic expression which will represent your mathematical function, your function model. So let's really try to look at some application problems. All right, here is an example. You're choosing between 2 texting plans. Plan A has a monthly fee of $15 with a charge of 8 cents per text. Plan B has a monthly fee of $3 with a charge of 12 cents per text. In the first part, part A, we want to express the monthly cost for Plan A as a function, and the function f is to represent the number of text messages in a given month, x. All right, so let's do this. So we're going to call the function f. So we have f of x. So the cost in a month for Plan A would be, so the monthly fee in Plan A is what? $15. So that's 15 plus a charge of 8 cents per text. So a charge of 8 cents per text. and let's say times the number of text messages for that particular month. So what we have done here is express the monthly cost for Plan A in terms of a function f. We obtained f of x is equal to 15 plus 8 cents times x. In part B, you want to express the monthly cost for Plan B. And that cost is going to be expressed as a function of g. All right, g, and again, we're going to let x represent the number of messages per month. So what do we have? So we're going to call it g. G as a function of x. So g of x is equal to, let's go back to Plan B. Plan B has a monthly fee of $3. All right, that's fixed. You have to pay that monthly fee with a charge of 12 cents per text. So let's say, so it's the monthly fee plus 12 cents times the number of text messages in that given month. So the function that represents the monthly cost for Plan B is g of x is equal to 3 plus 12 cents times x. Part C, how many text messages will the cost for the two plans to be the same? In order for the cost of the two plans to be equal, that means then that we want f of x, which represents the cost of Plan A, g of x, which represents the cost of Plan B. What do we have to do then? So we merely just need to equate them, because when will the cost be the same? So it's when f of x is equal to g of x. So what do I have? 15 plus 8 cents 0.08x is equal to, now g of x, 3 plus 0.12x. And now we want to solve this for x. So if we solve this for x, 15, 3, if I transpose the 3 to the left-hand side, so I have 12 is equal to, if I transpose 0.08x to the right-hand side, that's 12 cents minus 8 cents is going to be 4 cents, 0.04x. So this is what I have so far. And we need to then solve for x. We want to now solve this equation for x. So I'm going to divide by 0.4 on both sides. 12 divided by 0.04. If we do the division, we get that x is equal to 300. So therefore, we conclude that the plans cost the same for 300 text messages. Let's consider another example of an application problem. Functions, using functions with formulas. The problem reads, a machine produces open boxes using rectangular sheets of metal measuring 15 inches by 8 inches. The machine cuts equal sized squares from each corner. Then it shapes the metal into an open box by turning up the sides. All right. Part A. Express the volume of the box, V, in cubic inches as a function of the length of the side of the square cut from each corner, x in inches. The first step is to actually, if you can, always draw a diagram. So what do we have here? We have a rectangular sheet So let's see what's happening. We have a rectangular sheet. All right, we have a rectangular sheet that measures 15 by 8 inches. The machine cuts equal sized squares from each corner. So let's see. So it's going to cut from each corner. And let's say that each square measures X. This is X. So from each corner, we're going to cut equal sized squares. So this is X, this is X. This is X, this is X. This is X, this is X. All right, now I'm going to shape the metal into an open box by turning up the sides from each corner here. So after cutting equal sized squares from each corner, the open box looks like this. And what we have then, so the length, we've cut X on this side, X, and a box of X inches on each side. So then the length now becomes 15 minus 2X. And this is now 8 minus 2X. And the height here is X. All right. So, in part A, it says express the volume of the box as a function of the length of the side of the square cut from each corner. All right, so we let X represent the inches to be cut from each side. So we know that the volume of a box is the length times the width times the height. And we want to express V as a function of X. The length of the side cut from the length of the side of each square cut from each corner. All right, so we're going to write V of X then is going to be, now the length of the open box is 15 minus 2X times the width, 8 minus 2X, times the height, X. All right, let's simplify this. So now we have the volume expressed in terms of X. So simplifying, we have, let's first do the multiplication. We can use the FOIL method. 15 times 8 is 120 minus 16X minus 30X. And now a negative 2X times a negative 2X is a positive 4X squared times X. Multiplying, we're going to get 120 times X is 120X. So here we get a negative 46. A negative 46 times X is a negative 46X. And finally, 4X squared times X is 4X cubed. So what we have, expressing the volume V as a function of X, we have 4X cubed minus 46X plus 120X. X times 46X, that's 46X. So when we multiply X times 46X, we get 46X squared. So the volume expressed as a function of x is given by 4x cubed minus 46x squared plus 120x. Part B. Find the domain of V. All right, let's see what's going on. Since x represents the inches to be cut off, so x represented the inches to be cut off. So in other words, x has to be greater than 0. The smallest side is 8. The smallest size is 8. So since the smallest side is 8, we must cut less than 4 inches off of each side. Why is that? Because look what happens to this if x is greater than 4. You get a negative quantity, and we're dealing with distance, the length, which has to be positive. So in other words, x has to be greater than 0 and less than 4. So therefore, the domain of V is the set of all x such that x is greater than 0 and less than 4. Or in interval notation, we can express this, the domain as the open interval from 0 to 4. In this example, we would like to model the area of a rectangle with a fixed perimeter. The problem reads, you have 200 feet of fencing to enclose a rectangular garden. Express the area of the garden A as a function of one of its dimensions x. So again, let's draw a diagram. It's a rectangular garden. Length times width. We have 200 feet of fencing. In other words, to enclose the rectangular area. That means that the perimeter is 200 feet. And we know that the perimeter of this rectangular garden is going to be 2L plus 2W is equal to P, but P is 200 feet. So let's solve for L. Let's express L, the length, in terms of the width. So 2L is equal to 200 minus 2W. Simplifying by dividing both sides by 2, we have that L is 100 minus W. So this is the length expressed in terms of the width. So we now want to express the area as a function of one of the dimensions x. So let's let x represent the width. All right, I'm going to let x represent the width. So now we know that the area of a rectangle is length times width. So we can now write this as, so this means that this is now 100 minus x, because we're letting x represent the width. So the area then is x times 100 minus x. But it says express the area as a function of x. So I should be writing a of x. So a of x is 100x, x times a negative x squared. And of course, area we have what? Square units, so this would be square feet. So we've expressed the area of the garden as a function of one of its dimensions, x. So a of x is equal to 100x minus x squared, square feet. In the next application, we're modeling simple interest. Simple interest. You may recall that interest is principal times rate times time. All right, this is the formula for computing the interest. So let's see what the problem is. You place $25,000 in two investments expected to pay 7% and 9% annual interest. Express the amount of interest I as a function of the amount of money invested at 7% x. We're going to call that amount x amount. So since it's annual interest, we know that T is 1. So I have interest is P times R. All right, let's see. Let's see what we have in the problem. So we're going to let x represent the amount invested at 7%. Let y represent the amount invested at 9%. So together, you're investing X amount in one account, Y amount in the other account. Now there are two ways we can approach this. I like to, let's tabulate the information given. It helps you to keep track of the important quantities. Let's identify the accounts by the rate. All right. One, you are paying 7% at a rate of 7%, and the other 9%. We're using the formula principal times rate. So principal and rate. So at 7%, we're investing X dollars. That's X dollars of the 25. In other words, together, X plus Y should be $25,000. So if I invest X dollars at a rate of 7%, then I have Y is going to be 25,000 minus X dollars. So I'm investing at 9% an amount of 25,000 minus X. Now the rate. The rate on the 7%, that's going to be 0.07 and the rate 9%, 0.9. So what do we get over here? So principal times rate is the interest. So here's the interest accrued from each account. So the interest on the 7% account is x times 0.07. 0.07 times x. The interest on the 9%, so we have the amount in this account, 25,000 minus x times the rate. So the rate is 0.09 times the principal. 25,000 minus x. So the question is, express the amount of interest I as a function of the amount of money invested at 7%. We invested X dollars at 7%, so that function should be in terms of X. I of X, then the interest, the total interest from this investment is then going to be the interest from the first account, which is going to be 0.07x plus the interest from the second account, which is 0.09 times 25,000 minus x. So we have expressed the interest earned, the total interest, as a function of the amount of money invested at 7%. So here is the interest, the total interest.